we studied translational motion. Compared with rotational motion. This object moved from one place to another. But with rotational motion, the object changes the direction it's facing. It turns. They're really similar and have a lot of similar qualities. More importantly, an object can do both at once. If you throw a football, it spins and changes from one place to another. If you throw a frisbee, it's spinning. It's also moving from one place to another. In those two cases, how fast it's spinning isn't connected to how fast it's going, right? It can be spun, and that's one thing, and it's also moving from place to place. That's another thing. But there's also rolling. Rolling is something that is spinning and changing location at the same time, but those two things are connected. How fast it rolls probably determines how fast it goes. So we're going to have to study all of those types of motion, but we're going to focus right now on just talking about how we describe rotation. And remember, we did that for translation too. Our description included a group of variables that we used to articulate how things move. 4 of them were vectors, and I'm super confident you remember what all these things are. So one's about changing location, displacement, initial and final velocity, and acceleration and time. We studied these under the precipice of uniform accelerated motion. Remember me saying those words? The idea here was that it's uniformly accelerated. The A was constant. We did constant acceleration problems. In fact, we developed a whole set of equations, didn't we? Starting with a trapezoid and working our way out, and we came up with 5. I'm not going to write all 5 here. I'm going to write, 3. Look familiar? Remember way back in September when you thought physics was hard? Then you found out the reality of that wasn't the hard stuff? In fact, I think some of you would like to return back to when it was just this hard. That look familiar? They should all look familiar to you. Again, I'm only going to put a few of them in here because if you'll notice, we tended to use the same couple over and over again. And we use these the most, didn't we? But there are others, right? There's 2 others. I just didn't put them up there. This is the one that's missing displacement. This one's missing final velocity. This one's missing time. But there's one that's missing acceleration, and there's one that's missing initial velocity. Remember? You have that note card somewhere in your notes? If not, you should probably find it. For rotational motion, we're going to have all the same variables, all the same things, but we're going to use different symbols to represent them. So, for example, instead of delta x, we're going to talk about the displacement of an object based on it changing the direction it's facing. So that's an angle measure. How many degrees did it change? So for angles, we use theta. So delta theta will be the angular displacement. Now, angular displacement is going to be like in degrees or rotations or radians. That's how we'll measure angular displacement, and we'll barely ever use degrees. It's really going to be rotations is probably the big one will tend to be for delta theta. Now, you'll notice that because we're dealing with an angle measure, and because traditionally angles we use theta for angle measures, physics decided that they're just going to use Greek letters for all of these variables, and that's how you differentiate them from their linear counterpoints. So instead of V, we're going to use the Greek version of V, and that's omega. Omega is just a W with a little bit of flair. So, and we've talked about omega already. We talked about it a little bit when we talked about centripetal motion. But instead of using, and this is going to be, I don't think this is a surprise, but these will be angular velocity. This will be things like rotations per minute, or rotations per second, or radians per second. That's generally the units we will use for those. And if we have a change in velocity, I don't think it's a huge stretch to figure out we're probably going to have a symbol for acceleration. So we'll use the Greek letter alpha for A. I think it makes sense, doesn't it? And we'll call this angular acceleration. Units, radians per second squared mostly. It could be rotations per second squared too, but it's usually radians per second squared. And t, which, not a vector, but also got to be the same. All this stuff takes place in some kind of time interval. Now, we're going to be talking about things that do the same stuff. I want you to watch this again. I'm going to get it up to some initial velocity. That's the initial velocity. You notice that initial velocity is changing? So there's going to be a final velocity. And is it taking time to do so? And it made a certain number of rotations while it was doing it? You're getting this, right? That this is going to be all the same kinds of things that we did before. So I don't have to do all the graphing and stuff to convince you that eventually the area of some trapezoid and the slope of some graph is going to be related. Do I? Do you remember doing all that before? I don't want to do that again. I want to say, look, it's going to be the same thing. It's uniform accelerated motion. So instead of VF equals AT plus VI, it's going to be omega F equals alpha T plus omega I. Do you see what's going to happen? You'll have a set of equations for translational motion, and you'll have a set of equations for rotational motion. So I don't think I should have to do this. I'll do the next one just for funsies, though. Where I see x, I'm going to put theta. Where I see a, I'm going to put alpha. And where I see v, I'm going to put omega. But I expect you can do the rest on your own. Take your 5, make a new equation sheet just for this. Does that make sense? Now, there is one difference, and based on the time, I'm not really going to say much about it, but let's see if you can help me out a little bit. What direction is the fan spinning? Not to me, it's not. When it comes to direction, these are all still vectors. And I think, I baited you, right? I knew you were going to say clockwise. I knew I'd be able to say, because I'm standing over here, that no, you're wrong, and we can't just use clockwise and counterclockwise. It's also because in a minute, you're going to be so happy because you get to bust out my door. The door will open. Does it open clockwise or counterclockwise? You understand how that doesn't make any sense for the stupid door? So we'll need to come up with a way of describing direction too. Luckily, you don't have to come up with one. There is one already. You'll just have to learn what it is. All right, study tonight, folks, please. Study tonight.